Hello and welcome to my class. My name is Mr. Johnson and I am in space and physics. You don't need much for this, you just need a pen, piece of paper if you want to take notes. I'm just going to share my screen with you in one moment. Okay, so what should we do by the end of this lesson? By the end of this, you should be able to describe and explain how the tilt of Earth's axis gives rise to the seasons, and describe the development of key ideas to our understanding of the structure of the solar system. So let's go on our first objective. This is our picture of the solar system, a classic solar system. It's familiar to most people of any age. It's a huge turf in space, a huge area that contains the planets and celestial objects that are so familiar to anyone who's ever watched the sky at night on BBC or looked at a book on astronomy. Our solar system contains the sun. That's our star. The planets, moons, asteroids, and comets, where asteroids are pieces of space rock that are floating around in orbit around the sun, and comets are sort of dirty ice balls that fly in and out of our solar system, but are pretty much held in place by gravity. So how do all these things interact? I've already mentioned something to do with this. The bodies of the solar system are moving around at very fast speeds, and I do mean very fast. So why is it that the sun seems to rise in the east and set in the west on Earth? Why does the moon seem to go around the sky at night? If they move so fast, why don't they just fly off into deep space? The answer is gravity. Gravity is a force that can act over a long distance. It doesn't need to touch an object to push or to pull onto it. The bigger an object is, the more mass it contains, the larger and stronger its gravitational field, the sun. So what do I mean by gravity? And what's this thing that we're talking about called orbit? Well, there was a thought experiment done a long time ago. The idea was having a big enough cannon on Earth to see from space. So let's get that cannon in there. And if we fired a cannonball, we don't fire it fast enough, eventually it'll move, but it'll fall back down to Earth with a thump, pulled back down by Earth's gravity. If we fire it a bit faster, then it'll travel further around the Earth, but eventually it'll still fall enough, not so fast that it shoots off into space, but just fast enough, then the cannonball will not fall down to the ground. However, it won't have enough speed to fly away in a straight line, as Earth's gravity will keep pulling on it to change its direction. At this point, the ball will always be a state of falling around the Earth, and it will keep moving around it in a circular path. This circular path is what we call an orbit. So when we're talking about orbits, it's a circular path that a body takes around another due to gravity. And it's these orbits around the sun, around each other, that form the organisation of the solar system. Here's our solar system. It's the classic model that we all have seen at some point in our lives. The sun is at the centre of the system and is the largest body with the planets move in circular, and not even necessarily circular, but elliptical or pathways called orbits around the sun. They're moving fast enough to not fall into the sun, but they're not moving fast enough to fly away. The sun's gravity is constantly just pulling at them that little bit to make them go round. This is our solar system in 3D, top to bottom. And you can see that most of the planets are in orbit or line, with one exception. Mercury, which is this planet here, closest to the sun. Venus, the second planet. Earth, our third planet from the sun. And Mars. Now, these are the planets of the inner solar system, and they're present inside the asteroid belt. That's the marker for the inner solar system. Outside, in the outer solar system, beyond the asteroid belt, we have Jupiter, which is the biggest object in the solar system that is not the sun. Saturn, Uranus, Neptune, and these are the classic 8 planets that make up our solar system. You may also know of Pluto and other dwarf bodies such as Ceres and Makmak. They're classed as dwarf planets, and they're at the very edge of the solar system. So this is the organization of our solar system. Planets can also have things orbiting around them. We call these objects natural satellites or even moons. For example, we all know you look up at the sky at night, you see our moon. Earth has one moon. It moves around us in orbit due to Earth's gravitational field, constantly pulling at it. Other planets also have moons, but they don't just tend to have one. For example, Jupiter, the largest planet in the solar system, has at least 79 known moons today. Let's identify the different bodies that make up the solar system. Question 2, or outcome 2, describe and explain how the tilt of the Earth's axis gives rise to the seasons. So what's important to know is that the Earth is divided into 2 halves, or hemispheres, which are separated by an imaginary line called the equator. Our continent, Europe, is in the northern hemisphere, which is the top half of the Earth. And it's important to note that our North Pole and South Pole are not straight up and down between the middle. It's off at a tilt. Because of this, the weather in Europe is very different at different times in the year. The Earth's axis, that imaginary line that runs through the North Pole to the South Pole, is tilted at an angle of 23.5 degrees. The Earth rotates once every 24 hours around this axis, and this is why we have day and night time. As it's rotating, the side that's facing the light, the sun, is in daylight, whereas the side facing out into space is in night, but that will move around to face the sun, so they will have day, and the other side will go into night. Earth in seasons then. We have 4 seasons: spring, summer, autumn, winter. Earth moves around the sun in its orbit. It takes 365 days to make one complete cycle, or 1 year to make one complete orbit of the sun. It never changes the direction of its axis. Its axis is always pointed in the same direction. This means that the Earth is always tilted the same way in space, no matter where it is around the sun. For example, if I use my laptop case as a good example, pull this up so I can see. If I take this and tilt it like so, and this is the sun, as it's moving around, the laptop case never ever changes its orientation. There or there, it's still angled the same way. Now this is important because it means at this point, the bottom of the case is closest to the sun. This point, the top part of the case is closer to the sun, if you like. And this is what gives rise to the seasons. Sometimes the North Pole is tilted closer towards the sun. That's our summertime. Sometimes it's tilted away. That's our winter time. When the North Pole is in summer, the South Pole is in winter, because if the North Pole is tilted towards, the South Pole is tilted away. Other times, the tilt of the Earth is not pointing towards or away from the sun, but into space itself. And this will be when the sun's here and it's gone from looking like this to moving around to the side like so. It's not tilted forward or backward. So it's receiving the same amount of light and heat on the north and the south hemisphere. This is a straightforward example of it on a diagram. When the northern hemisphere is tilted towards the sun, over here, it's summer in the UK. This part of the Earth is closer, whereas this part is tilted away from it. On this side, the southern hemisphere is tilted towards the Earth. It's receiving more light and heat, whereas the northern hemisphere is tilted away. Over here, the tilt would not be towards away from the sun, but to space. So the amount of heat and light from the north and southern hemisphere would be the same, and that would be the same situation here at this point. So we've got winter, spring, summer, autumn. Changes in heat and light due to the seasons. In the summer, the sun feels warmer in the summer compared with the winter because it's higher in the sky. This means that the heat from the sun is more concentrated on the ground. Summer days are also warmer than winter days, as the sun is shining for a longer time because it's higher up in the sky, so it has further to rise and further to fall before it passes into nighttime. This gives it more time to warm up the air and the ground. The converse is true for winter. The sun feels colder in winter compared with the summer because it's lower in the sky, because the Earth is tilted away from it, or should I say northern hemisphere is tilted away in its winter. The sun rises and sets lower in the sky than it does with respect to summertime. This means the heat from the sun is less concentrated. Winter days are also colder than summer days, as because of that lower arc, the sun seems to be shining for a shorter time, so it has less time to warm up the air. Let's describe and explain how the tilt of Earth's axis gives rise to the seasons. Final bit, describe the development of key ideas that led to our understanding of the structure of the solar system. This, at Key Stage 3, is quite straightforward, it's quite simple, but it leads on, if any of you are interested, to further discussion of the detail when you do triple physics, for example. So our modern solar system. Opposite is a picture of Earthrise. This was the photo of Earth taken by astronauts on Apollo 8. They were also the first people to see the side of the moon that faces away from the Earth. We now use a model of the solar system in which the sun is at the center. The planets move around the sun in orbit. In this model, the planets are revolving around their axes, which explains night and day and why the sun seems to move across the sky during the day. How did we get here? Well, scientists nowadays, astronomers, have spacecraft and very powerful telescopes to explore and observe the solar system. We can literally send things up to hover over them with cameras and show us what's going on. Early astronomers didn't have access to this technology. They could only make observations using their eyes. So because of that, they could only describe what they could see with their naked eye. This meant that in early astronomy, the only 5 planets that were visible from Earth were Mercury, Venus, Mars, Jupiter, and Saturn. So how did this affect their model, the early model of the solar system then? Well, first off, we have an Egyptian fellow called Ptolemy. And Ptolemy's model was one of the earliest to try to make sense of the structure of our solar system. He proposed what came to be known as a geocentric model. So geo meaning Earth and centric meaning centered, geocentric, Earth-centered model. In this, he placed the Earth at the center, no surprise, of the solar system, with the sun and the other planets orbiting around us in perfect spheres. The stars were fixed in spheres at the edge of the sky. Ptolemy's model was refined by Aristotle and accepted for the next 1500 years or so. It explained why the sun seemed to move around us in the sky during the day and rose in the east and set in the west. It was constantly going from that point in the sky to that point. It went around us. This must be because the sun was moving around us. Also explained why we had day and night. If the sun was moving around us, then when it's on our side, daytime, when it's around the other side, nighttime. Also seemed to explain why the planets moved around us in the nighttime sky. Because the planets were moving around us because we're at the center, they must be going around the sky too, just like the sun. Ptolemy's model was accepted for the next 1500 years or so. It explained why the sun seemed to move around us during the day, rose to the east and set to the west, why we had day and night, and why they moved in the sky. But the problems with some of these observations, it didn't explain the seasons. Couldn't explain what was going on there, why we had autumn, winter, summer, spring. It also didn't explain why the planets sometimes seem to move back in the sky on themselves. This is called retrograde motion. This was important for making predictions about where the planets would be or where stars would be for navigation and planting. And this is a time-lapse photography picture of a planet moving in the night sky, and you can see it seems to move back on itself in a kind of zigzag before it moves forward again. Its direction of travel going from this to this. And astronomers couldn't explain why it seemed to do this. Later, astronomers built on and corrected the ideas of Ptolemy. In 1543, there was a Polish astronomer named Nicholas Copernicus, and he published a book, but he was so worried about the impact of what his book was writing that he published it close to the time of his death so as not to kick up a fuss. In it, though, he suggested a new heliocentric, where helio, or where it's to do with the sun, was named after the Greek god of the sun, Helios, and centric again meaning centered, so heliocentric, sun-centered model. And no surprises here, he suggested that the sun was at the center of our solar system, and that the Earth, planets, moons all moved around the sun in circular orbits. It explained away some of the problems that Ptolemy could not. It explained away seasons, phases of the moon, but it still could not explain why we could not predict where the planets would be with accuracy in the night sky, or, if you like, this retrograde motion, why they seem to go back on themselves. So, Copernicus's ideas were not accepted straight away, partly because he couldn't explain those observations still. Then a guy called Galileo Galilei came along and made some very interesting observations with his telescope to prove things one way or the other. Now, this is an image of Jupiter, and in it you can see moons moving across the surface of Jupiter. And Galileo sat there with his first very primitive telescope looking up at the moons at Jupiter in the night sky, and he watched the moons transiting across its face. He saw moons and he watched them seem to disappear on one side of Jupiter and then reappear on the other, and then move across the face, just like these two are doing now. Now, the only way this could be explained is if those moons were orbiting around Jupiter. But the geocentric model said everything orbited around the Earth, including the moons. So this was direct proof that actually not everything went around the Earth. And so set us on the idea that if these objects, these moons, could orbit Jupiter alone, then the heliocentric model must have been correct, because this could not be explained by a geocentric model. Galileo also went on to view the phases of Venus, which also proved that it was not orbiting the Earth. The fact that Venus has phases like the phases of the moon proved that there was something getting in the way, which meant that Earth, it could not be going around Earth in orbit. Big problem still, it didn't explain that backward seeming motion of planets in the sky. That came later with a guy called Johannes Kepler. Kepler's model best explains the observations that we have made about objects in our solar system, such as why we have day and night in the phases of the moon. He kept the sun at the center. The heliocentric model was correct for him, with the planets and the moons, planets moving around it and moons moving around the planets now. But he said that orbits were not perfectly circular. There was no such thing as the perfect circular orbit. It was more like an ellipse, a squash circle. Think of an oval shape with a kind of narrowing at the top, or if you get a perfect circle and squash it down, you get oval shape, rugby ball-like. This explained the retrograde motion of the planets in the sky then, because when it was going past the squash part of the cycle, it would have seemed to have gone backward on itself to go around. And it finally helped settle the evidence for the structure of the modern solar system. Now we had a model that could explain all the observations we could make. And that is our third outcome: describe the development of key ideas that led to our understanding of the structure of the solar system. So I'm going to say thank you very much for listening. I hope you've enjoyed this lesson, and I hope to see you again. But for now, take care and have a good day.